David Bruce. I work in the general industry and automotive segment, where we're in between sales and engineering, and I'm responsible primarily for iRVision. Me and my team support integrators and end users and ASIs with their iRVision needs. So today we're going to talk about how to deal with some common issues in 2D iRVision applications. Here is a list and a quick agenda on what we plan to talk about today: calibration, best practices for both robot and fixed mounted cameras, uh, issues after everything's calibrated, where the part, when you set your reference position and then you translate the part, it appears to work fine, but when you rotate the part, it doesn't, and talk about why that happens and things that can be done to alleviate that problem. GPM training, just go through some best practices on when you're teaching the GPM how best to do that. Talk about image logging and how to take advantage of the image logging and even log images without affecting cycle time, which historically is a big problem. And talk about the part Z height, which is a necessary attribute in the vision process that, if not inputted correctly, will cause some problems. And then just briefly on what's available, what support is available on demand through the CRC site, both our resources link and our iRVision forum. Okay, with that, get started. We'll dive into calibration. So for a robot-mounted camera and for a 6-axis robot, you always want to use the automatic grid frame set feature of iRVision. It's included with iRVision. It's not a separate option. You get to it via the utilities menu on the iRVision screen. And what that does is it defines the user frame for you, the user frame for the calibration grid. So you always want to use automatic grid frame set when you have a robot mounted camera. Now, when you go through the automatic grid frame set, it both defines the user frame for the calibration grid, but it also spits out a tool frame for the camera, which is defined that the Z value is basically based on the start point that you teach that initial start point at. And then the orientation of that tool frame is what you see here, with Z pointing back at to the camera and then X and Y aligned with the grid. Now, you don't need this tool frame for iRVision to work properly, but it does come in handy both in setting up a quick recalibration and applications that I myself have implemented. It's kind of handy if you have a tool frame you can use to use offset positions or calculated positions to move your camera to specific areas in the cell. It can be handy, but again, it's not required, but it does come out of the automatic grid frame. So there's a close-up of what the orientation of the tool frame looks like when you're done. With a robot mounted camera, it's very easy to do a two-plane calibration, so you should always do a two-plane calibration. That gives you the best perspective calibration possible. So I always do two-plane. And then once you're done doing the calibration, you use automatic grid frame set to define your calibration grid. You want to set up a calibration program, a TP program, to do the calibration should you ever need to do it again. And here's an example of it right here. You can use the user frame for the grid and the tool frame for the camera. So that way, this position here could be all zeros, and it'll put the camera directly over the center of the grid. And that's a great spot to do your first calibration plane. And then you can move up or down from there, generally about 50 millimeters to do your second calibration. And there you have a two-plane calibration, and you can run this program whenever necessary to recalibrate, and it's always best to leave the grid fixed in the cell somewhere. Put a cover over it so it doesn't get dirty, but if it's fixed in the cell, you don't need to rediscover the user frame for the calibration grid. You can just simply run this program if ever you need to recalibrate. Even if the camera gets damaged, you can put a new camera on there, set the optics back to what it was before, run this program, and you'll be recalibrated and good to go. You would not need to reteach reference or anything like that. For a fixed mounted camera, really the best thing is the robot generated grid calibration. That's also comes with it's part of iRVision. It's not a separate option. You get to that through the iRVision utilities menu as well. And it's the best way to calibrate a fixed mounted camera, especially one with a large field of view. The calibration target used for the robot generated grid cal, here's some examples. You want it to be large enough that the vision system can find it easily. So a good rule of thumb is 100 by 100 pixels, depending on your field of view. And it needs to be obviously asymmetrical. Now, a perfect circle can work. It does work. I've used it, but you're really not supposed to. You're better off using something that's has some obvious asymmetrical to it. It's not completely symmetrical. Otherwise, it could maybe find the origin of the part a little different if it flips the orientation of it. So you want something that's obviously asymmetrical and about 100 by 100 pixels as your target. As you see here, we're using in this example, just using two perfect circles, some distance apart. Now, one thing when you're doing the robot generated grid cal and you're teaching the GPM, you want to put that teach window as small as possible. You don't want to just use a big window when you define it, because it actually uses that window size when it goes through and builds the grid. And if your window is too big, then you're not going to get calibration points into the corners of the field of view. So you want your teach window for the GPM to be as small as possible to define the pattern you're using. And one thing I found doing is, well, there's 3 steps to robot generated grid cal. There's the target position where it gets a tool frame for the target. Then there's program generation where it generates a TP program, and then you run that TP program is the 3rd step. For the target position measurement, I found shrinking the search window by just in the calibration, just simply hitting set here on the search window and shrinking it will help the target position go a little faster. And then once you're done with that, before you do program generation, you'll want to set that search window back to the full window, or just to the area where you're going to be working. You don't need to calibrate the full field of view if you're only going to be working in a certain area. So you can actually limit your calibration just to say if it's a table you're picking parts up on and your field of view is a little bit bigger than the table, you can just limit your search window to the table. And then the TP, so there's the last step is a program generation spits out a TP program, and you run that TP program to actually do the calibration, and it actually goes through and builds 2 grids, 2 different planes, and that's how it calibrates the camera. Now, once this TP program is created, you can actually modify this program. You can change the orientation of positions, you can add positions, you can move them up and down, you can do whatever is necessary to say get the field of view, to get the target into a certain area of the field of view that it can't get to with a default orientation. Because once you have the tool frame defined for the target, it knows wherever that target is, and it'll get a valid calibration point. So this program can be modified as needed. Points can be added, deleted, or modified. And if the target is left in the same spot on the tooling, recalibration can be done by simply rerunning that TP program. If for some reason the target is moved, maybe it's got to be taken off, or it was just a temporary sticker. If you put that sticker back, or you put it back roughly close, all you need to do then is just the target position. Just rerun this step. That'll redefine the tool frame, and you can just go and rerun the TP program. You would not need to do the program generation again. So it's just a handy fact. And the U tool is updated from the target position when the calibration TP program is executed. So this will dump a position into a tool frame, into tool frame 9, say, or whatever you decide. But that isn't updated. It's updated from this target position at the time the TP program runs. It doesn't write to tool frame 9. You could use tool frame 9 in the interim and change it to something else. But as soon as you run the TP program, whatever is calculated here gets put into tool frame 9 or whatever the tool frame is that you selected. So one of the 2 calibration planes when you're doing robot generated grid cal should be as close as possible to your working surface, to your offset frame. And sometimes that's difficult to do because when it does the target calculation, it needs to do some off-axis rotations, and you can, end up, interfering with the offset frame with a fixture or something. So that means you need to teach your start position up higher, which puts you further away from your working surface. So one way to get around that is to go ahead and teach it higher, but then just set your plane spacing to a negative number. So what that'll do is it'll do all its target measurement stuff at the higher level, and then when it does its second plane, it'll go lower than that start position rather than higher. The default is plus 100 millimeters, but you can make that a negative number. And then that second plane, where it doesn't do any off-axis rotations, will be closer to the surface you're working on, and be a little bit better at calibration for what you're doing. So this will put one of the calibration planes closer to the working area. Okay, so that's best practices for calibration, both robot mounted and fixed mounted. Now we're going to talk about what happens when I set my cell up, I set my application up, and my part works fine when it's just translated around, but once it rotates, there's issues. So it's a classic issue here. So say we've set up our part. There's a camera up above here you can't see. We've set our reference position in Vision. We've taught our reference position in the robot. We go ahead and we translate that part. We just move it in X and Y in the offset frame, and we run our vision, and lo and behold, the robot goes right back to the taught reference position on the part. Works great. But then when we rotate the part even a little bit, it's no longer very accurate. We're off. And why is that? So this usually occurs with a manually taught calibration grid frame. And the reason for the issue is the error in where the camera saw the calibration grid frame and where the robot defined it. So any error there is going to show this issue, right? It's not going to show up in translation because a millimeter is a millimeter is a millimeter. The spacing of the grid, as long as you enter, 30 millimeters or 22.5, whatever the grid spacing is, then it'll handle a translation, no problem. But once you start getting rotation, then where that grid was plays a major factor in the math, and then you see this issue. So it's directly related to a poor definition of the user frame grid. Either the way it was taught, you can see here, it was just sloppy teaching. You didn't have the pointer quite over the center of the dot when you were defining it, or one of the other 2 points that define the frame, or maybe the tool frame being used to define the grid was not very accurate. It wasn't checked. You didn't rotate about it and make sure that the TCP for the pointer was accurate. Or another issue I've seen, or something that can happen, is you can take great care to come up with a nice accurate tool frame for your pointer. But then when you teach your calibration grid frame, you don't have that you don't have that TCP active, or that tool frame active. So you can see here, the pointer is defined as tool frame 1, but when you're in your user frame teaching it, you have tool frame 3 active. So all those points are going to be way off. So that's something else to keep in mind when you're manually teaching a user frame for calibration. So when you get this issue, first thing you want to do is make sure there's nothing wrong with the mastering. Robot mastering, obviously, if it's not mastered properly, then its accuracy is not going to be very good, and that will obviously create this issue. Then you want to check your calibration grid user frame and pointer TCP, used to define the pointer TCP, and if at all possible, use automatic grid frame set or robot generated grid cal. That'll alleviate the problem right away if you're able to do that. But if for whatever reason you can't, go back and define all those things. Now, still at the end of the day, even if you have a perfectly accurate tool and user frame, sometimes this issue still will come up because robots are not inherently perfectly accurate. They're very repeatable but not accurate. So there always is some discrepancy between where that grid is and where the camera saw it. So if you take care to do all those things and you still have some rotation error, depending on the robot you're using, that could still be there. There's a program called Adjust Offset, which is part of the Vision support tools. And what you can do is you can use that to kind of you can try to use that to apply a fudge factor for when the part is rotated. And here's how you use it here. So here you find your part, you get your offset, and you call Adjust Offset. And what this does is it takes so the first argument is whether or not you're using a position register or vision register for your offset. And then this is what index has the input offset. Is it VR1 or PR1? The third argument is what PR stores the fudge factor, which is an X and Y value. The fourth argument is what is the new offset going into. And in this case, it's VR2. And then this is a register for if there's an error when this is called. So basically what happens is you get your offset, you run it through the fudge factor, and it puts it into VR2, and you use VR2 then to do the motion. So the way you set this up is you put your part down, you teach your reference position, then you spin it 180, you let the vision bring it back, you can see it's off, and then what you do is you play around, this is all based on the offset frame, so you put some values in here, you run it again, you see if it gets better or worse, and you basically tune these numbers till you get it as good as you can at 0 and 180, and then you'll have a little bit better accuracy when parts are rotated. And this will work for tracking applications, for IR pick tool applications as well. Often this is because you often can only do a single plane because the camera is upstream on the conveyor, and that's your only option is to do a single plane calibration and manually touch up the grid. So this can come to play if required, if absolute accuracy is required when parts are rotated. So that's that issue. Now moving on, we're talking about some GPM training and best practices for that. So you want to work, I would like to say this before, you really, as a lead-in for any iRVision application, you want to work with a machine vision lighting supplier to engineer the correct amount, configuration, and color of LED lighting. You do not want to depend on ambient lighting for your application. If you depend on ambient lighting, then your application will most likely fail. Machine vision requires dedicated lighting, and all applications are different. There's no silver bullet when it comes to lighting. There's many different lighting companies available. We have contacts at all of these. There's many different lights available, and you want to make sure that working with them we find is the best way to get the correct light specified, and then you can go ahead and purchase the light from them. So if you don't use the correct lighting, per the application, you're going to have issues, especially when it comes to highlighting edges that you're hoping to train and locate via a GPM. So assuming you have good lighting, now what are the best practices for defining a GPM? You want to use as few edges as possible to completely define the part. There's a G-edit feature which has been around since about 8.2, I believe, 8.2 software. But you want to use that because you can define perfect edges right in the model. So rather than depending on the model having perfect edges, you can add those perfect edges right into the model. And I'll go through a little demonstration and show you how to do that. But you can add lines, rectangles, circles, arcs, those kind of things. There's also a learning function that's also been around since about 8.2 or maybe 8.3, where you can, using a logged images or right at setup time, you can capture a bunch of images of the part at different angles, and it'll kind of help you automatically decide which edges aren't found that often and could be eliminated, automatically masked out. And I'll show you that in the demo as well. And then there's an emphasis area. So if there's certain small features of your part that you need to be found every time, you want to make sure you use your emphasis area to emphasize those. Otherwise, that area may get ignored because most of the part is found except this little area, but maybe that little area defines a clocking feature or some aspect of the position and orientation of the part. So you want to make sure you find not only the whole 70% of the whole part, but maybe 70% of this little part, and that's what the emphasis area can do. So on the GPM screen here's where you get the G-edit through this button here. The learning, which I'll go through, that's done here. You hit start, and we'll go through how to do that. And the emphasis area is right here as well. So, and this is all with the new R30IB Plus software, by the way. So this is 9.1 software. So let's go to RoboGuide here to do some training. So I have a RoboGuide cell here. I'm just using my virtual camera, my new virtual CXV camera, looking at this connecting rod. So we will go in here, and I'll go ahead. I'm going to just create a brand new GPM so we can train it from scratch. So what I'm going to do is I'm just going to go ahead and I'm going to use G-edit. So to define this part, really, there's a large circle and a big circle, and that's pretty much enough information. So I'm just going to go ahead and hit G-edit and select the area that I want to use G-edit in. And the first thing, I'm going to go ahead and add this circle. So I'm going to put it up here. So what I'm doing is defining a perfect circle for this circle here. And let me blow it up a little bit so I can get the correct size. So I'll size there we go. And then when it defines it, it gives you these arrows. These arrows point to the light, to the polarity of the edges from dark to light or light to dark. So these arrows point to where the brightness would be or where the light side would be. So we want to invert that because obviously the brightness is on the outside. So that's that one. Oh, I'm going to go back in. I'm going to add another one for the small guy. Zoom in again. This guy right in the middle. So again, we're adding some perfect edges to our part. So now we have two circles. We could stop and find, and look at that. We find it, and we even find some mistaken ones here, right? So that's because this little circle, it doesn't take up much of the pattern, so it finds the big circle, and it just assumes these are off in space. So we'll go ahead and use our emphasis area to say, hey, I want to make sure that when you find it, that you find that guy as well. So now we're able to find our part. Just going to turn down the contrast a little bit. So now we're able to find our part, not finding it. Hang on one second here. Okay, let our size vary a little bit. I'm not sure why it's not finding it. Hang on. Oh, I know. Sorry. So we're going to edit the next one. We're going to edit. There we go. Yes, so I forgot to invert the polarity of the edge. So we can see here, okay, and then we're going to invert. That's what I forgot to do. So now the polarity of our edge is correct. So now we can find the part and we can find the emphasis area is working. So we can move the part around a little bit in RoboGuide. We'll move it, rotate it, go back, and there we go. So now we're able to locate the part using as few edges as possible, just using the large circle and the big circle. That gives you position and orientation, and we're using gedit. We're using perfect edges to help find that. So that's how gedit works. Now talk a little bit about the statistical model train. So here we have I've recorded these, so these are actual live images, which I recorded earlier. So you can see here we're getting scores, so that guy's not even found. Some of these aren't found. We're getting scores that are close to 80, sometimes in the 70s. So what we'll do is we'll go ahead and we'll start our learning. And we're going to use images that have already been logged. So it goes through and you pick, you can turn, if you don't want to use this image for whatever reason in the logging, in the training, you could turn that off or you can turn it on. So you go through, you select which images you want to use. It goes through, decides, okay, these are the images where I can find the part. Um, and then it says, okay, here's here's the percentages of how often all the edges are found. And you could actually, in this case here, we'll make it nice and strict. So we're going to say, you know what, if the edges in all those images, if an edge isn't found 90% of the time, then I want to get rid of it. So we're going to get rid of a lot of edges that were not needed. And we're going to finish. Now here's our updated model. And you can see here our scores are much higher now, right? So it kind of did it. And even in instances where the part wasn't found, it's we're able to find it now by using this statistical model trainer, this learning. So that's a feature that's been around for a long time. A lot of people don't know about, and it's pretty handy. Okay, so that is GPM training best practices. Now I'm going to talk a little bit about image logging and how to log images without affecting cycle time. So normally logging images to the file after every run find statement can cause the TP program to be delayed quite a bit, and a lot of people don't like to use it because the interface to the logging device, to the USB stick or the M card, especially if that card is full of files, it can take a while. So people don't use logging because of that, and logging is really pretty powerful. So, and here's of course how you enable logging through the iRVision config screen. But there is a sort of a backdoor method that FANUC told us about a couple years ago that they did called the high-speed logging. And right now there isn't a switch in the iRVision config screen. There will be soon, but you can still take advantage of it. It's a little convoluted to get to it. So you need to go to system vars, and there's the vision config flag. You need to set it's a bitmap is what it's called. So you need to set a certain bit, and the way you do that is you add this number to whatever this value is, and that enables high-speed logging. And what high-speed logging does is whenever there's an image to be logged, it's written to DRAM. The TP program, is allowed to move on, and then some other task will actually take that image off from the DRAM and write it to the log device in the background. So it enables you to keep going, and it doesn't slow down the application. Now, if several snap and finds are done back to back, when you have this high-speed logging on, then when you get to about 10 images, that the sort of the buffer that's being used will be filled up, and you will start to see a delay. So it's not for 100 images in a row, but several will work quite well. And there's even a Carol program added that can be called to make sure, hey, I want to make sure this buffer's empty before I start doing a series of snaps. That's called iRV wait log. So if you call that, then the program will not continue until that DRAM buffer has been exhausted. Now, the best results we've seen for logging is when you use high-speed logging in combination with PC file share. So what PC file share is an option that allows you to write files to a Windows shared drive on a PC via the Ethernet network on the robot. So when you use high-speed logging in combination uh, with PC file share, you can see that we can log in about 100 milliseconds. We can log images. Now, when you go over 10 images and you get up to 20, then that goes up a little bit because there is some time added to clean out the buffer once the buffer gets filled. But still, much better than not using high-speed logging or not using PC file share. So PC file share, it's an option that comes with the internet connectivity customization option. Here's what it looks like on the CPL. You basically define a client tag through the teach pendant, And then you give it an IP or a host name for your PC, and then a share path, and then a username and password if necessary. And then that just becomes another device that can be used for backups and all kinds of things, including logging. So it's very handy. And setting up the PC file share can be tricky depending on what version of Windows you're working with. That's all explained in this manual here. There's a whole chapter on how to set up PC file share. So we'll just go into back to RoboGuide and just show you a little bit about um, what can be done with logging. One of the handy things, so to see the log, there's a right from the main screen, there's an interface to the log, an application that allows you to see all the images if you're logging all images and the data. You get all the data, and you can sort by different, if you have different processes, you can sort by the different processes. You can sort by the date. If you did things on a different date, you can do that. So there's none of those. And we'll go back to the conrods. So here's all the conrods. You can sort by, time or event. So you can really see all the stuff that's happened. And then, of course, all the data is here as well, including the offset and everything. So that's kind of handy. But I think the real advantage of logging is right in the vision process. You can go ahead and hit this playback button. And what you do there is it'll give you all the images from the log just for that vision process and the date and time that each one of them happened. So really, this is great if I'm helping a customer who's having issues. I'll say, send me a robot backup. I'll generate a robo guide from that, and I'll say, okay, take some logged images and send me the log. I'll put the log in the correct spot in the virtual robot, and then I can do what I'm doing here, and I can look at all the different images. I can go to the next one, the next one. You could actually just sit and watch it and go through them all. So if there's an issue with something, you can go ahead and you can go into your GPM. You could change your settings, make sure it works for that one. If I turn this off, then obviously I'm not going to find anything. I can turn it back on. Can make sure it works for the problem image, and then make sure it works for all the other images. So it's really a very powerful tool that I find some people, not a lot of people know about how the log works and all the different things you can do with it. So and if you want to go back to the camera, you just hit the camera, and now you're back onto the camera. So, image logging and the interfaces to the log, I find are really very useful for especially troubleshooting issues that come up after a system's been running for a while, or experiencing lighting changes or part changes. Maybe the color of the part has been changing. If you're able to log images, it can help quite a bit getting to the root cause of some problems. Okay, and then finally, part Z height. Talk a little bit about the part Z height and just exactly what that is. So, perspective calibration allows for an accurate XY location to be discovered for parts at different distances from the camera, right? Basically, with 2D vision, as parts get further away with traditional lenses, uh, the they're going to look smaller, and as they get closer, it gets bigger. That's because the millimeters per pixel changes the further you get away from the camera. So in order for iRVision or any vision system to accurately calculate an XY position, it needs to know the camera part distance. We need to know how far the part is from the camera in order to accurately calculate that. And the way iRVision does that is through what's called the part Z height, and that's in all 2D vision processes in iRVision. And the way it does that is so the part Z height is the distance from the offset frame of origin, so whatever your offset frame is, wherever that origin is, to the GPM feature that you're looking at in the Z dimension only. So what is the height of the feature in the offset frame? And by knowing that, it can calculate the camera to part distance because it knows where the camera is for calibration. It knows exactly where the camera is. It knows where the offset frame is. That's a user frame that you've defined. And then you tell it that dimension in Z, and then it can figure out the camera distance. So it's just a much easier way to figure out that camera distance. If you actually had to measure the camera distance, the distance from the feature to the camera, that could be very cumbersome and difficult to do accurately because often the cameras are mounted up high to get the required field of view. So the part Z height is a generally easy thing to measure and enter. But the point is, it needs to be accurate. Otherwise, you're not going to get accurate information. So I got a few examples here just to illustrate exactly what it is. So here's our offset frame at the top of the table. Here's our camera looking down at it. So in this case, the part Z height, the correct part Z height is 75 millimeters, which just happens to be the the side, the the length of this cylinder that we're looking at. If our offset frame was up here for some reason, then our part Z height would be negative 75, maybe, right? The offset frame needs to represent the XY plane that the part's moving around in. It has nothing to do with where the camera is. It's how the part moves. It's 2D vision. It's going to give you an XY value. So the offset frame needs to represent that plane in which the part's moving around. And then the part Z height is the distance of the feature in that, in the Z dimension in that offset frame. So in this example here, we're using world. For whatever reason, we're using user frame 0 as our offset frame. So in this case, the correct part Z height is 239, right? So you can imagine if you were using world in this particular application and you entered 75 rather than 239, you're going to get a very different answer and you're not going to be correct. So it's important that you understand what the part Z height is, and that it's entered correctly. In this case, where we have a table off at an angle or a fixture off at an angle, we have our camera also at an angle, so we're nice and square to the surface. So our offset frame represents how this table is sitting relative to the robot. In this case, the part Z height is the same, 75 millimeters. Here we have a camera at an angle, so the cameras, you can do that. Ideally, you want your optical axis and your offset frame Z axis to be parallel. That's the best configuration, but sometimes just plain not possible. With perspective calibration, you can certainly put the camera at an angle. Through calibration, the robot knows what angle the camera is at, and it can still give you accurate information, but when the camera's at an angle, the part Z height is even more critical. But again, in this case, the offset frame specifies how the part is moving around. It doesn't specify what the camera is. It specifies how the part moves around. So in this case, the offset frame is the same, and the part Z height is the same, 75 millimeters. For tool frames, when you're doing a tool offset, so if you're looking down the robot picks a part blindly and shows it to a camera to get accurate information to then load a fixture or something. So in that case, you're generating a tool offset. In that case, the part Z height is relative to the tool frame, not the offset frame. The offset frame is a tool frame in this case, but the same rules apply. So in this particular case, we're looking at this corner for this application. The tool frame is the default tool frame, so it's just all zeros. So that means Z is pointing out of J6 from the center of the faceplate. And for this particular application, our feature is 185 millimeters below the faceplate. So the correct part Z height for this example would be 185 millimeters. If you put 0 in there, you're not going to get the correct information, and it's not going to be accurate. In this case here, we'll have this connecting rod here. So the connecting rod's at an angle to the faceplate. So you want to have a tool frame which represents, what the Z-axis is pointing to the camera. And so the tool frame has been defined for the ID grip of the small hole here, and the Z-axis pointing straight up. So here it was defined the actual TCP, the origin of the tool frame, is at the bottom of those two grippers, and then our feature ends up sitting about, in this case, 22.2 millimeters above that. So if you're doing a tool offset for this application, the part Z height, the correct one would be 22.2. So those examples, I think, kind of illustrate how to calculate the part Z height and what it is. That concludes all the things I was going to talk about. I just wanted to, in conclusion, mention that through our CRC site, if you go to our CRC site and you go to products, there's a vision link there. That'll bring you to this page here. There's some product resources, there's some CAD files, different things under product resources. There's our a lens calculator, which is a PC application that allows for the calculation of what your field of view is going to be for different lenses. It's very powerful. If you don't have that, go ahead and get that. There's also a moderated user forum there where you can post questions, you can search questions. You do need to set up a separate account for that. But it's a fully moderated, fully searchable forum. So if you're having trouble getting answers, start with the iRVision user forum. You may find the answer in there already. Feel free to answer questions that are on there. It's fairly active. And then there's a knowledge base, which has some white papers, technical reports, that kind of thing. That's actually, there's not much in there yet. We're working on that, but that's another resource that's available if you have a CRC login. And then also on our FANUC America YouTube channel, we have an iRVision playlist that has some small and longer videos. Actually, most of the webinars we've done, the FANUC Friday webinars, have been put up there. Typically, a few months after this one, we'll put it in the ASI area initially, and then after that, we'll move it out onto our YouTube channel. So they're all there. There's about 11 of them, I think. That have been up there for a while, and they're free for you to go and look at, and you can start and stop as needed with all kinds of different a different topic. So be sure to check that out. You might find something that you didn't know about. And with that, I will say thank you very much for watching and see if we have any questions. Is anything being done to more accurately calibrate robots from the factory? Good question. So there are some, uh, there, I guess the answer is yes and no. There are some robots that you could get calibration done at the factory or even done here. There's a Leica calibration we can do to make a particular robot. It's not available for all robots, but some robots we can do a Leica calibration where we can get it to be a lot more accurate, the absolute accuracy. Through IR calibration, there's vision mastering, which you can do, which the user can do. And that just looks at a grid from a bunch of different ways and tweaks the mastering from J2 to J5, which will give you a more accurate robot because J1 and J6, when it comes to absolute accuracy, are redundant, don't matter. So there's stuff you can do on your own with vision mastering. There is signature analysis, which can be done here. And I believe you can even order some of those units from the factory already signature analyzed. So just work with your, your FANUC salesperson to figure out if the model you're interested in supports that or not. Another question here, is the Plus software GPM faster? Yes. With R30IB Plus, probably a lot of you haven't had a chance to use it yet. As you saw in the screenshots and my demos, the interface is different, and yeah, the software, the CPU on the R30IB Plus controller is essentially the same CPU, but it's faster. It's a faster clock rate or whatever. So yeah, the GPM, it's about depending 20 to 30% faster just in raw times. You have the ability to bin the image. Right now, any image. Sony cameras have gone away, so there's a new CXV camera, but you can bin it 1, 2, 3, or 4. So you can either take a quarter, an eighth, a 16th, or a 32nd, or a quarter, an eighth, a 16th, or a 32nd of the amount of pixels when you do your analysis. So if you have a really large image and a really large part, you can set your binning to say to 1 or 2, and what that does is it just effectively reduces the resolution of the image and makes the GPM run faster. So that's available through the Snap tool, which is a new command tool with iRVision, and that will make it run faster. Okay, with that, I'll turn it back over. Oh, sorry. One more question here. Do you still need to use a pointer for calibration in IR Pick Pro for the grid when camera is upstream of the robot? Well, in IR Pick Pro, you really don't need to calibrate the camera. Um, you really don't need to calibrate the camera with IR. If you're talking about IR Pick tool, yes, you still need to use a pointer. There is an auto grid frame set or an auto track frame setup which uses a camera. So in that case, no, you don't need to use a pointer. I'm not sure if that's released yet on IB Plus. I think it is, but in that case, you put the grid down, you move it to the robot. It uses a robot-mounted USB camera to find the grid and actually do the track frame and the camera calibration all in one. That's auto grid frame set, and I would talk to your salesperson to find out more about that, or send an email to visual tracking at FANUC American. Someone can get back to you with that. Another question here: what is a typical cycle time in iRVision? Well, that's a hard question to answer because that obviously it depends on what you're looking at. The fastest I'll say with R30, the snap time is just the raw image transfer time on R30IB. For a high resolution image, which we call high resolution 1280 by 1024, was somewhere in the neighborhood of, I think, 140, 150 milliseconds. That's just to get the image in. You got exposure after that. With R30IB Plus, because of the new vision interface, it's a coax vision system. It's so the Sony has gone away. It's a whole different vision system, which is 4 times faster. So the image transfer time is about 4 times faster. So we're down to about 40 milliseconds plus exposure just to get the image in. So right there, for a high speed image, for a high resolution image, we're cutting out about 100 milliseconds. And then to find a blob or a GPM, a blob can take 10 milliseconds. A GPM can maybe take 30 milliseconds, 50, depending on what kind of degrees of freedom you have set up. It can scale up quite a lot from there. But the raw image transfer is much faster. So yes, you're going to be the fastest you'll be able to do anything at full resolution is about 100 milliseconds. Whereas with R30IB, it was closer at full resolution to 220 milliseconds. So yes, it is definitely faster. With that, I'll turn it back over to Derek. Thank you very much.